Welcome to Chapter 3, Part 3. We just finished up discussing how we can use ARIO to analyze the stability of conjugate bases and therefore predict the strength of acids. And you should definitely go practice that with your homework, and there's an extra practice set on eCampus for you. When we compare these different acids, what we want to also remember is the pKa isn't going to lie to you. So if you have available quantitative data, that is to be believed, right? There are going to be examples where ARIO does not work out when compared with actual the physical data, the quantitative data. And for one, I promise I will not give you any questions to trick you. If there is pKa data there, you look at that first. If there is not pKa data, then you can assume, if I'm asking you the question, that you can use ARIO. There are going to be some examples given here, right? ARIO is a guideline of priority, and it sometimes fails, and that's okay, right? Again, this is supposed to be useful to help us to predict strength, to help us later on understand reactivity. It is not so that we can choose an acid when we go into the lab, right? Again, if pKa data is available, we go with that. So for instance, when we look at the reaction of acetylene and the amide ion here, what we can do here is say, okay, so this is acid, base, and then this is the conjugate base, and this is the conjugate acid. Right, so if we look at pKa's, we can tell, right, the lower pKa is the stronger acid, and equilibrium favors the weak side, so the products would be favored here. But if we were comparing the bases, we would come up with something different, right? Because if we looked at the bases, nitrogen should be able to hold that charge better than carbon, right? Because nitrogen is more electronegative. But we also get the combination with the orbitals. And so when the reality comes, when we see actual experimental data, the pKa isn't what we would have predicted following ARIO. So for some acids, we simply just need to know the pKa, and that's okay. Again, I won't try to trick you on anything graded. When you're working your homework, that's something to keep in mind. Watch out for questions that say, go look it up in a table, right? It'll usually reference a table from your book. If it's telling you to look up the pKa, look up the pKa. All right, but to practice with our skill, because we are going to want to qualitatively analyze protons in this, or acid strength, there's going to be different ways to do it. We've done several practice problems where we compare two acids. There's also practice problems like what we see here, where we're not comparing two different acids, we're comparing protons on one compound. So for instance, if we're trying to decide which of these two protons is more acidic, you're still going to follow the same strategy. Look at the conjugate bases. If we removed the red proton, right, we would wind up getting the negative charge on the oxygen. Whereas if we removed the blue proton, we would wind up getting the negative charge on the carbon, right? Different atoms. Oxygen can hold that negative charge better than carbon can. This is going to be more stable, right? Making it the weaker base, meaning that our stronger acid or our more acidic proton would be on oxygen, right? So we can apply the same qualitative methods. We can apply ARIO to protons on the same molecule, or we can compare two different acids. We'll go through the next example here. If we remove, let's go back. There we go. If we remove this red hydrogen here, and leave that one on there, we get this conjugate base. If we remove the blue hydrogen, let me go back there. I need to redraw this. We have 1, 2, 3, 4 carbons, 5 carbons. We're leaving the hydrogens in the middle carbon alone. There we go. We get the negative charge out here. They're both negative charges on carbon, but if you practice drawing resonance, and you should do that as you're preparing for exam 1, this would have 2 more resonance structures, right? You would be able to share that negative charge on both oxygens and the carbon. The one on the right has 1 additional resonance structure, right? You could share the negative charge with this oxygen, but because this would be a CH2, you can't skip around and go to the other oxygen. So 2 resonance structures are going to be more stabilizing than just 1, or 3 total versus 2 total. So this would be more stable, which makes this red proton more acidic. That actually comes up in chapter 21. So we will keep talking about this throughout Organic 1 and Organic 2. I definitely recommend you can go find the practice the skill problems and work through this one. If you go into Wiley Access and go into your chapter 3.4 module. We can also test this skill by predicting equilibrium positions. So instead of asking you which acid is stronger or which proton is more acidic, you could be asked to predict the equilibrium. So you're going to have an acid and a base, and you're going to have a conjugate base and a conjugate acid on the other side. And if you have pKa data, well, then that's easy, right? What you need to know is that the equilibrium favors the weak, right? So the weaker acid and the weaker base will be on that. They're the more stable acid and base. They will be the side that the equilibrium favors. Now, if you have the pKa, right, the higher pKa would be the weaker acid, and so that would be the side that would be favored. If you don't have pKa's, right, so with quantitative methods, you compare pKa of the acid. For the qualitative method, you are comparing the stability of the bases, right, using REO. So here we would be comparing the base and the conjugate base. Oh, I'm sorry, I circled the wrong thing. The base and the conjugate base. All right, so for instance, let's see. Well, okay, not for instance. There's not a practice problem on the next slide. You can work on your skill builder. 3.11, and there's some practice problems on eCampus and in your homework. I just want to go over something here. Equilibrium arrows are frequently drawn where the top arrow and the bottom arrow are the same length. Just because it's drawn that way doesn't necessarily mean that the products and reactants are in equal proportions. A lot of times that is just meant to show that there is a significant amount of reverse reaction, right? It's not going to completion. However, if you're trying to predict which side's being favored, you may be given this double arrow, the equilibrium arrow where the top is longer, or the equilibrium arrow where the bottom is longer. All right, so if you have these as options, you're saying that you're getting equal proportions of product and reactant. If you see the arrow to the right is longer, the right side is favored, right? That's going to be where you have the weak, right? The weak base and the weak acid. If the arrow pointing to the left is longer, right, that means the left side is favored. And so that's another way to practice that skill of comparing acids and bases using REO. This can be important also for us as chemists on a practical level. For some reactions, you really need to deprotonate a reagent. And so picking an acid that is strong enough to do the job becomes very important. We're going to see, especially when we get to like chapter 9, where we need to deprotonate acetylene. So a triple bonded carbon with a hydrogen. We have to pick a strong enough base, and our most typical bases aren't strong enough. And so that really becomes important to us. Now, you're not going to have to make the decision based on pKa, based on acid strength. We'll go over the appropriate choices when we get to those reactions, but that is an important part of our day-to-day life in the lab. And so understanding chapter 3 it's like a basic building block for us, a very standard building block. You can skip leveling effect. We will not be discussing that. You won't have any homework or test questions, so you can skip through 3.7. Solvating effects, we'll just quickly discuss here. There are some very, there are things that create a large difference in pKa and acid strength, and you can see the effects when you think about REO. A is more important than R. Resonance is a bigger effect, has a bigger effect than induction. Induction has a bigger effect than orbital strength. Solvating effect is even smaller, and so it's not included in REO. But look right here between terbutanol and ethanol. When you look at the conjugate bases, the negative charge will be on oxygen. There is no resonance. There's no inductive effect. That's different. There's no orbital effect. That's different. The only thing that's different is just the general size of this guy. And so when you have that negatively charged oxygen, another stabilizing effect for that charge would be hydrogen bonding or ion dipole interactions, right? So the positive side of water is going to form a hydrogen bond to that negatively charged oxygen. And you can just get more water molecules around this smaller acid, this smaller conjugate base here when you remove that proton. And so it does lower the pKa. So it's interesting. It's not going to come up for you very frequently. You'll be able to stick with REO. But that's all that solvating effect is. It's just the more your solvent molecules can get around that conjugate base, the more stabilized that negative charge can be. And there's kind of a better picture of it. You can see from the electrostatic potential map, it's like that negative charge is more exposed when you have less organic molecules sort of being bulky over here. It's called a steric effect. We're going to talk a lot about sterics in chapter 4 and chapter 5. Counter ions. Now, this is something that you may not be tested over per se, but this is very important to our communication as chemists, as organic chemists here. You learned about net ionic equations in Gen Chem, right? So the reaction may be sodium amide and water react to form ammonia and sodium hydroxide. But this isn't an aqueous solution. Sodium amide would be Na plus and NH2 minus in water, right? Water isn't going to dissociate. This is going to form ammonia and sodium hydroxide, which does dissociate to form sodium ions and hydroxide ions. We don't include the counter ions down here in the net ionic equation because the sodium is unchanged, right? It is a counter ion. It could just as easily have been potassium or lithium, and the reaction really doesn't change at all. So they're frequently left out. And you learned all about that in Gen Chem. Net ionic equations can be useful because then we're focusing on just the part of the reagents that are reacting. Now, where can this get confusing? When we're looking at reactions, you are frequently going to see bases being used, like sodium hydroxide, and it may be written as NaOH, or it may just be written as hydroxide. And again, we're leaving out that counter ion. What is important for you to recognize is that this is an ionic bond here. People forget. When you see sodium, you've got to recognize that's going to be an Na plus and an OH minus. We also frequently use sodium methoxide, NaOCH3, and sodium ethoxide, it's CH2CH3. What you want to start recognizing is that's going to be the methoxide ion or the ethoxide ion, right? The Na is there, but it is just a counter ion. You can't buy a bottle of negatively charged ions. It is always going to have a counter ion so that it's overall neutral, right? It's an ionic bond, so that Na plus is floating around, but it's not what we're focused on. And that will continue to come up as we get into reactions where we use bases, which will come quickly, especially in, I think, Chapter 7 is where we start getting our first organic reactions. And then we'll have, in our last video, Part 4, we will have a refresher and discussion on Lewis acids and bases.